Welcome to Mastering Solutions. In this question, there's a couple different ways that we can think about it. I'm going to show you two different ways. And the first way is going to be the fast, easy way of thinking about it. I'm going to show you a longer way, and it's maybe a little bit more thorough of a way, but you'll see that we get the exact same answer with both methods. The equation that we'll be using to solve for this is going to be the image distance is equal to n2 divided by n1 times the object distance. So we're solving for the image distance. And so I like to think of it as the start of the person, or where the object starts, is essentially the height of the person in a way, right? Now don't get that confused with the height of the image. We're solving for the object distance here, but that's kind of how I think of it. And so when we list this, we are going to have the N2 in this case be air, which is going to be 1, obviously. And the N1 in this case is the water, the 1.33. And they tell us that this person is 1.8 meters tall, which will be the object distance. We can use that in this case because we're standing directly over them. So as we look down, that's essentially going to be object distance, the height of the person. And the image distance, the start of the image, is going to be the new height of the person. So that's why we can use the object and the image distance, when normally you would think, well, it should be the height, right? When we plug in the numbers here, we have S prime is equal to N2, which we said is 1, divided by N of water, 1.33, times the object distance, which we said is 1.8 meters. Here's 1 divided by 1.33 times 1.8. And so that gives us 1.35. And so 1.35 meters. This is the short way to figure out the answer of that's how tall the person's going to be for this question. Now, a more thorough way, I've seen this question a couple different ways. What you can also do is we can use the same formula here, but we'll do it twice. We can solve it for the image distance for the top of the person, their head, and then we can do it a second time for the image distance of their feet. In order to do that, we have to think about this pool. It's 3 meters deep. So if this is 3 meters, and they say that the person is standing on the bottom of the pool, right? And so we'll say they're all the way down here, and this is the 1.8 meters, of course. So the difference between these two, the 1.2 meters, that is the distance that we're going to use for the image distance for the top of their head. And then the image distance for their feet is going to be the same distance as the top of the pool, because we're sitting on a diving board, sitting essentially right at the edge of the water, right, looking down at them. And so when we do this twice, we're going to have the image distance of the head is equal to same thing, 1 over 1.33. And then in this time, we're going to do 1.2 meters. And for the feet, we'll have the same thing again. Only now we have the 3 meters. So now when we take these two, I'm going to show you them at the same time. So first, let's do the 1.2 meters for the image distance of the head. And now let's change this and do the image distance for their feet. Now what we have to do is we take the difference between these two, and that gives us the height of the person in the water. Only if you see here, if we take them and I don't round it at all, you're going to see that it is the exact same as the answer that we got for the short method. So there is no difference here out to 1, 2, 3, 4, 5, 6, 7, 8, 9 digits, right? So it is the same. They are 1.35 meters tall in the water. So this is two methods of thinking about this. We take the object height and then we multiply it by the ratio of the indices of refraction to give us the image distance, which in this case, since we're directly above them, gives us the height. Or we find the distance to the head and we find the distance to the feet, and the difference between those two is going to be the height, of course.